So on the campus of Paris-Saclay, we can often come across this small blue-white car equipped with all kinds of sensors on top, and also with safety engineers sitting in. And this is autonomous vehicles on open road test. And the open road test of autonomous vehicles is not only permitted in Paris. In fact, all over the world, in United States, in UK, and in China, governments all make regulations about the open road test of autonomous vehicles to help boost this technology. But before its commercialization, there still exist a lot of challenges for us to save. For example, from its acquisition module, the challenges often is based on the problem of camera and all other kind of sensors. And to its perception module, there are challenges about the mapping and localization problems, and until the control and accreditation module. And for my thesis, I work on this decision module, so which is to help autonomous vehicles to make the best decision based on a driving scenario. So it will tell the autonomous vehicles to accelerate, to brake, turn left or turn right based on a specific driving scenario. And among all of those possible trajectories, we want to get the optimal trajectory which meets our needs. And we can use this optimal trajectory as a reference to evaluate the different modules of the autonomous vehicles and to help us to make the validations. And if we look at how the autonomous vehicles to gather environmental information, we know that it has all kinds of sensors, including camera, lidars, radars. And because of various reasons, the information they gathered of some kind of uncertainty. And maybe it's because of the bad weather, of the precision problem, or the complicated environment. And one challenge for us is how to model this kind of uncertainty properly and to help us get better results, to help us build a more robust trajectory. So the objective of my work is to help build an optimization model, which takes the scenario information as an input. This input can include all kinds of different uncertainties. And this input passes to our model, and our model will generate the optimal trajectory based on our needs. So here, I just give you a simple example of the driving scenario. And this driving scenario is the ACC, Adaptive Cruise Control, which is quite common in our daily life. So in this driving scenario, often we have our ego vehicle. And our ego vehicle with all kinds of sensors will detect the position, the speed of the vehicle ahead. And we also want to keep an optimal distance to follow this vehicle. And here, we have an objective, so which is to keep a reference distance, which is based on the difference of the speed and the difference of the position. And in the meanwhile, we also have a lot of constraints. For example, we have some minimal distance constraints to avoid any potential collisions. And we have some maximum velocity constraints, which are based on the traffic code. And other constraints for the passenger's comfort, etc. And all these objectives and constraints, it can be translated mathematically into an optimization problem. So when we formulate this input, this all kinds of variables and data into the mathematical problem, we can solve it to get a list of commands, which can also be used to build a trajectory. So above, this is we can call it a deterministic model. But in real life, as I have explained before, the information always involves uncertainty. And here, in my work, the arrows are modeled by random variables. Here is an example of the normal distribution variable. And maybe you can model by other kinds of random variables based on the statistics. And for objective function, we transform it into its form of expectation. And for the constraints, instead of using the traditionally constraints, we replace the traditionally constraints with a chance constraint. And this is a constraint that can guarantee that the probability of a constraints is ensured and the probability is above a certain level, which means that the safety can be ensured by these constraints. And this model includes the uncertainty. And so we can compare the performance of those two models on our generated driving scenarios. Here is just an example of our numerical results, which is the histogram of the number of violated constraints in the two models. So the red bar represents the stochastic model, and the blue bar represents the deterministic model. And we can observe that by the results of stochastic model produce less violations of constraints, which means that the trajectory is more safe. So here, as conclusion, so we can see that the stochastic optimization, so it's quite a useful tool to optimize the trajectory of autonomous vehicles. It can help us to have the trajectory with more robustness and more safety. And in the future, or currently, I'm also working on these applications of this stochastic optimization in other various driving scenarios and with other type of uncertainties. And hopefully we can get better results and to help develop the autonomous vehicles into a new level. Okay. Thank you.